Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we move on to talk about atomic spectra and energy levels. So spectroscopic analysis of light given off by excited atoms show only photons of particular energy are given off. And so this allows us to identify elements, and now we're going to talk in particular about the hydrogen atom. And so when we talk about the hydrogen atom, we want to talk about Bohr's atomic model. And so this is Bohr's model. Basically, in order to explain the stability of an atom, Niels Bohr gave a new arrangement of electrons in the atom in 1913. So according to Bohr, the electrons could revolve around the nucleus only in certain orbits, as shown here, in 1, 2, 3, or 4. So basically, these energy levels means that energy is quantized, meaning there's specific levels at which it can be, and each orbit has a different radius. When an electron is revolving in a particular orbit or particular energy level around the nucleus, the electron does not radiate energy or lose energy, even though it has accelerated motion around the nucleus. So, from here, since there's no change in the energy of electrons as long as they keep revolving with the same amount of energy, when an electron jumps from a lower energy to a higher one, so let's say from the ground state up to an excited state, in that case, some energy is absorbed while some energy is emitted. When an electron jumps from a higher level, so let's say from the second excited state to the first excited state, the amount of energy absorbed or emitted is given by the difference of energies associated with the two levels. So from here, we can talk about the Bohr frequency condition. Bohr frequency condition. And this is the law that the frequency of radiation emitted or absorbed during the transition of an atomic system between two stationary states, basically ground state to first state or the second excited state, is equal to the difference in energy of the states divided by Planck's constant. So I just said that in words, but I can show you what it looks like in a mathematical equation. So delta E is Planck's constant times the frequency, or the frequency is delta E over H. So if I repeat what I said before, the frequency of the radiation emitted or absorbed during the transition from one electronic state to another is equal to the difference in the energy of the states divided by Planck's constant. So basically, the emission or line or atomic spectrum, depending on what textbook you're reading, they call it different things, for the hydrogen atom shows different groups of spectral lines, as you can see right here. So when you go from the n equals 2, or n equals 3, n equals 4, n equals 5, 6, or 7, all the way down to the first n equals 1 state, this is called the Lyman series. The Balmer series is actually the visible region. And those are these transition states from n equals 3 all the way up to n equals 7, all the way down to n equals 2. The Paschen series are up to n equals 3, and the bracket series are up to n equals 4. So for the hydrogen atom, we can actually calculate the energy depending on what the energy level is. And so that equation is En is negative HR, this fancy R, I'll tell you what that is in a second, over n squared, for n equals 1, 2, all the way up to infinity. So one thing I wanted to point out was that as n approaches infinity, so let's say infinity is all the way up here, we have n equals 5, 6, 7, 8, 9, 10, all the way up to infinity, the energy gets closer to 0. What that means is these lines get closer and closer and closer together. I'm not drawing this very well. But basically, the further up you go in energy levels and the closer you get to infinity, the energy gets closer to zero. So this only works for the hydrogen emission spectrum, and so we need a more sophisticated model for quantum mechanics that we'll talk about later. But in this case, when we talk about the atomic spectra of the hydrogen atom, we need to use this equation that I just showed for various calculations. So now let me tell you what each of these things stand for. So I said before that En is the energy of the particular energy level. H is Planck's constant that we went over before, but R, this is a new constant. This is called the Rydberg constant. And this has a value of 3.29 times 10 to the power of 15 hertz, which is a frequency unit, which is also the same as second to the power of -1. And then the N here is also the energy level. So now let's do a couple of calculations based on this equation.